You're listening to the NASA in Silicon Valley podcast, episode 64. Today, for the intro, I have Frank joining me again. Frank, tell us a little bit about our guest today.
Hey, Matt. Sure. Today, our guest is Adam Moreno. He was actually a fan of the podcast before coming to NASA. So it's kind of a cool thing to see that cycle of the podcast bringing people in and now putting that all back out there.
It was interesting after we recorded the session that he was like, oh yeah, I listened to all the episodes before, so this is kind of surreal. So yeah, it's nice coming full circle.
Totally. So yeah, Adam is a computer scientist by trade who now sort of sits at the crux between supercomputing and earth sciences, which is, I think, a really cool combination of skill sets because, you know, NASA does so much research on earth sciences and gathers a huge amount of global data. And so what Adam does is he works with a program called NEX, the NASA Earth Exchange, that works to bring those data sets and make them public. So any researcher anywhere in the world can make use of all of that data that NASA collects. So especially, you know, in this day and age, having access to all of that information about, you know, the Earth's climate systems and weather and all this different stuff can be really, really important.
Excellent. So we don't want to spoil it too much, but a little bit of housekeeping before we jump on in. You know, folks who are listening, you want to participate. We're using the hashtag NASA Silicon Valley on any social media platform you can think of. Also, we have a phone number that's 650-604-1400. Give us a call, leave us a message. We'll see how we can integrate that into the episodes. Also, obviously, if you've already found us, we would love for like review, comments, thoughts, suggestions, all that stuff. You can find us on all of the major podcast platforms, or you can grab our RSS feed and plug it into your own favorite podcasting app. But for today's episode,
let's hear from Adam Moreno.
Tell us a little bit about yourself. I mean, you haven't been here that long, but like, what brought you to NASA? How did you end up in Silicon Valley?
Yeah. So I'm from like a small rural town in northeastern Oregon. And then I went and got my bachelor's in computer engineering from Oregon State. Okay. Went into the Peace Corps for a couple years.
Nice.
And then went to graduate school for my master's at University of Montana. Okay. And there I was fortunate enough to have an advisor who super smart, super nice guy, and has been working with NASA for years now, decades now, on some of their Earth-observing satellite missions. And while I was there, he, I guess, got an invitation from NASA Ames to send some of his students to come here and learn how to use the supercomputer that we have here to be able to do, like cool Earth science.
And so even thinking back, I'm imagining, you know, spending time in Montana, which is like, it's called Big Sky, you know, like for a reason.
Yeah.
But even imagining like Peace Corps, I know from traveling overseas, if you go to some countries that are like, that are developing countries, not as much light pollution. I'm thinking Montana, not as much light pollution. So you just be like sitting back and looking at the stars, like just blow your mind.
Yeah, no, that's right. But you know, actually I think it's interesting because if you ask most people what they think about NASA or what comes to mind when they think about NASA, the first thing that comes to mind, of course, is space and, you know,
yes, of course.
You know, astronauts, space shuttles, and of course we do all that cool stuff. Yeah. But we also do a lot of cool Earth science as well.
Absolutely.
And so actually in the Peace Corps, this is where I kind of changed gears because I had a degree in computer engineering, you know, but then I went in the Peace Corps and I went like...
That seems kind of rare, going from computer engineering to go to the Peace Corps. Where did you go? What did you do?
Well, so I went to Paraguay and I was sent out into the jungle in Paraguay into a little community of like 300 people. I built my house there. I worked with the schools, farmers, students, all that sort of stuff. But what I think actually kind of changed my path from maybe a traditional engineering path to doing earth science sort of stuff is just, the majority of people who live out in the countryside in South America are subsistence farmers, right? You know,
totally.
They live off of what they grow, you know, and if they don't grow anything, their family doesn't eat.
Yeah.
And so things like droughts and heat waves.
There's high stakes.
Yeah, they're a matter of life and death, really. And so when I came back, I realized, I want to work on something that can, help actually the majority of the world, that are so tied to the environment that, yeah, it's a matter of life and death. And so I came back and I decided I wanted to study, climate-related issues, ecology related issues. And so, at University of Montana, actually, I studied forest ecology and ecological modeling. And ecological modeling just means taking like an ecological system, like a forest, turning it into mathematical equations, and then turning those equations into a computer model that you can then use to...
Yeah, and this is one of the cool things that NASA does. It's like, is the data collection. And then using the scientific community to turn data into knowledge. But gathering that data, it's not just from, satellite-based telescopes. There's, a lot of, data collection on the ground. And people always tend to think of, the larger climate, the big picture, Mother Earth perspective, but a lot of that data is used for agriculture.
Yeah,
even here in the United States,
it's
it's crucial information for even disaster response. You got to know how the Earth is reacting. It just that data that NASA collects pays dividends for all kinds of groups down the road.
Yeah, and that's right, and that's NASA's job, right? To understand this huge, massive, complex system that we're living on and in, and that we depend on, right? I mean, it hasn't been that long that humans have been able to actually study the whole entire globe.
Yeah.
Right? It wasn't until like the 70s that NASA and USGS sent up the first satellites dedicated to monitoring the environment, actually.
Yeah.
And also you need big computers to be able to understand what's going on. And that
So
also
much
hasn't
data,
been
yeah.
that long. So actually this is all relatively new science, being able to study continents, entire continents, or the entire global system altogether. But and so that's what I do here. But that was my master's, right? So
from Montana.
Yeah, I did my master's in Montana, and then for my PhD I went to Vienna, Austria.
Oh wow!
And I did my PhD over there. And my last year of my PhD, I came to AGU, which is this big, the American Geophysical Union here in San Francisco. And I knew I wanted to come to NASA. I'd been here before. I had some exposure. I was like, okay, this is where I want to be. And so I met with who's now Raman Amani, who's now my mentor here at Ames. And I just asked him, I was like, I want to come be in your group. Like, how can I make this happen? And he pointed me towards this fellowship opportunity that all NASA bases have. And so I applied for it, and I got it, and now I'm here. So
yeah, and you said just it hasn't even been quite a year yet.
No, not even a year.
Oh wow! And we were talking right before we came on doing this that you'd actually listened to the podcast before joining up.
Yeah, that's right. So
I'm going to be working there and better find out what people are doing.
Yeah, that's right. Yeah, so my last year of my PhD, I knew I was coming. And I wasn't really nervous. I was just kind of concentrating on my dissertation and defending. But then I stumbled across this podcast here, and that's when I got nervous, actually. Yeah. So, hearing about all the cool stuff all the smart people here are doing, and I was like, oh, okay, coming to the big leagues now. So.
Oh, fun. So you're working right now. Is it called Earth Exchange? Am I saying that right? Or
so the NASA Earth Exchange.
NASA Earth Exchange.
So, I work in a group called the NASA Earth Exchange, or NEX. And it's made up of earth scientists and software engineers. And so actually it's kind of a hybrid group of the Earth Sciences Division and the Advanced Supercomputing Division. Wow. Yeah, that's right. And so what NEX is what we call it. What NEX's goal is just facilitating Earth scientists to be able to use all of NASA's facilities. Like the supercomputer, and getting access to all of the data that exists in the world, actually. So we try to bring in massive data sets, bring it into one place, and then allow the NASA scientists, especially throughout all of the bases at NASA, to come and be able to use the facilities here. And then I think the longer term goal is to make it even more accessible to the general public at large. But like NASA has 10 to 12 bases, however you want to count it.
Different centers and locations.
Right, different centers. And, there's a lot of people doing all kinds of science there. But, maybe they don't all have direct access to the supercomputer like we do here at Ames. And so Nex's idea was just to help facilitate
that, because it's not only the researchers here, it's also NASA, as funded by the taxpayers, also goes through great effort to get that information also available to the scientific community. Because like it doesn't have to be like, we don't have to do it on our own. We can reach out to the larger group, and you almost kind of crowdsource, I guess, have everybody working and looking at these data sets, and then you just see things as they pop up.
Well, that's right. So one of the great things that NASA Earth Science does is they give out their data to the entire world for free, actually. And so this actually spurs science and innovation all over the world, because, as scientists here in the United States, maybe we don't focus on small countries like Paraguay or something. But if I'm an ecologist in Paraguay, Paraguay can't afford to have a space program, but they can get access to NASA's data to help them understand, their ecosystem, over there. And so that's one of the great things NASA does is gives away all of the data that we have processed, ready to use for free to the entire world.
Yeah, not too long ago we had one of the exoplanet specialists in here, and they're talking about, of course, traditionally when you think of NASA, you think of rocket launches, but you also think of like looking out into the universe, the solar system and beyond.
Yeah.
But they're telling the story of how, looking at a faraway star and how a planet will transit in front of it, and then you can confirm, yes, okay, there is an exoplanet around that star. You can see how that planet pulls on the gravity to get another idea of, like, you can start deducing, like, the density of that planet. But then she was also saying how if you capture that light right as it gets through the ring around that star, you have light that passes through that planet's atmosphere, and we can look at that atmosphere. You put it out on the spectrum and can start figuring out, oh, this is mainly made of oxygen, nitrogen. This is more carbon, or whatever the molecules or the properties. So you can really start to understand exoplanets and understand what they're making up. And I just immediately think of an analog of, like, the best example of a planet to compare it to is the one we're sitting on.
Yeah.
And so as much as we can understand what this Earth is doing and what it's made of, then that helps us be able to compare it to those exoplanets so we can confirm, are they really Earth-like planets out there?
Yeah.
And we know that because of what we know about Earth.
Yeah, no, that's right. So, that's another reason why NASA does Earth science, because we need to understand what's happening on Earth to be able to understand the other planets. And actually, one of the great things about being an early career scientist here at NASA is we have this early career network here.
Exactly.
And, part of that is we take tours of different places around Silicon Valley. We also have these happy hours and stuff. And, so during the happy hours, I've been able to talk with other scientists who are not Earth scientists, they're studying planets or whatever.
These are the newcomers too.
And they're doing like the cutting edge stuff, right? And there is a lot of overlap. There's a lot of people who are doing spectroscopy on other planets, and the same methods that they use are derived, maybe from the methods that were developed first to study the Earth, actually.
Yeah. And I think some of your work talking about, like, the supercomputers and software is also one of those natural ways to kind of pull things together, because it seems like whereas stuff may have been siloed, like, okay, you have earth science over here, you have, like, biosciences in one area, astrophysicists, or even aeronautics, but it seems that a commonality between a lot of these is becoming, like, computing, because everybody who's doing research needs that. It's like the supercomputer can help make better sense of the data.
Yeah, no, that's right. So, getting data from the satellite, like one of the satellites about Earth, that's super cool, and you can learn a lot just by looking at that data. But in Earth science, often what we do is we take data from all sorts of different sources, maybe several different satellites.
Okay.
And also
they have different instruments on it. They're looking at different things.
They're looking at different things. Maybe one is looking at the oceans, one is looking at the forests, atmospheres, cryosphere, so on and so forth. But then we also couple that with data on the ground. So in my case, I study forests. So I'll take, like, forest inventory data where people are on the ground measuring forests, along with weather station data and soil data. And then we try to put that all together to make something even greater than the sum of its parts, through maybe a big computer model that we need the supercomputer to be able to crunch all of those numbers to get a good picture of what's happening on a continent or on the global scale, things like that.
So talk a little bit about the forests, especially having lived in Paraguay for a while, you're in a heavily forested area, and like what happens there can affect the entire planet and a lot of times, or like the areas around it. So talk a little bit about how just the forests in general play into the global,
right.
Why
is a forest ecologist at NASA, right?
That's a good question.
So, there are several cycles that make up the global system. So there's the water cycle, the carbon cycle, energy cycle, nitrogen cycle, all these different cycles. Things that are moving around the Earth and make up really the system that we call...
that we live in.
Yeah, the Earth. And so if we're talking about something like the carbon cycle, global forests make up the largest terrestrial component of the carbon cycle. So, half of the carbon that goes into the atmosphere gets sucked down by forests. And so any large-scale changes to the forests can change the carbon cycle that could then change the climate cycle and have repercussions all over the world. Same with the water cycle and all of that sort of stuff. So
everything kind of interacts and
everything
ebbs
interacts.
And flows.
Right. So
like the food chain almost to a certain extent. It's like you tweak one thing and then other stuff happens even if you don't necessarily understand it right away.
That's right.
Things are all interconnected and interwoven, very complex.
Yep. Yeah. So I kind of say, well, like a computer is a very complex system, right? And it takes a lot of engineering and science and math to understand or build this sort of system. But the actual biggest and most complex system on Earth is the Earth itself.
Yeah.
Right? And we didn't engineer it.
No, yeah.
So that makes it even harder. So actually, we're just trying to figure out how this system works. And there's still a lot of work to be done. But so my little component of figuring out this system is figuring out how atmospheres and forests interact with one another.
Okay.
Yeah.
So you talk about like studying forests, doing that research, and then playing that into being a computer scientist is just like, this is an option for all computer scientists of like, you can also go study forests.
That's absolutely true. And we need actually more people with technical abilities to come and be able to make sense of this huge amount of complex data that we have.
So how do you do that? What are you doing? Like, what is your day to day?
What's
are you
my
running,
day-to-day?
or what are you running this data through like new software, through databases, visualizing it in different ways where you come up with newer ideas instead of it just being numbers on a spreadsheet? Talk about that.
So my day to day is like getting data from all different sources, satellites or the ground, and then transforming that data into something I can use. Maybe it's a map of a particular area like the United States that I want to study, and getting all of those data sets to match up, right?
Okay.
So they need to be able to be comparable and usable, no matter if they came from satellites or from the ground or what have you. And then I write a lot of code that crunches those numbers in the supercomputer. Maybe I'll have like a forest model that will get productivity estimates of the forest, given its reflectance from the satellite, given its climate, given the type of forest there is on the ground, and we want to know, well, how productive is vegetation all over the globe, for example. And so that sort of stuff goes through the computer. And so my ultimate goal right now, while I'm here at NASA, that kind of got me here, is I'm hoping to develop an early warning system where we can monitor all of the forests throughout the United States and pinpoint forests that are extremely vulnerable to a large-scale mortality event, whether it's from fire or beetles, or even just mortality without any sort of agent of death, like fire or beetles. And also understanding why those forests are vulnerable, and then giving some recommendation of what can be done to maybe prevent this large-scale mortality event. And so to do that, what I'm doing is I'm taking all of this data that I'm getting from the satellite, from the ground, and I'm writing code that will hopefully pull out equations, essentially, of the physics on how climate limits forests.
Oh, interesting. Okay.
Because,
what are the rules?
Yeah, what are the rules? Exactly. What are the rules? Because it's obvious, climate dictates what sort of forest can be where, right? So we have a different sort of forest here in California, in Silicon Valley, than we have up in the Pacific Northwest in Washington or Oregon, and that's because the climate is different. And the climate dictates all sorts of things within the forest. It dictates how tall the forest can get, how big the trees can get, how many trees can be in a forest, and things like that. But as of yet, we don't really understand how it limits all of those, or what this kind of curve looks like, depending on your temperature and precipitation, what sort of trees could exist in an area. And so I'm trying to pull out these biophysical limitations that climate places on forests, that I can then use to develop some sort of system that can recognize when a forest is out of balance with its climate system.
You've said it a handful of times, but talk a little bit about writing the code, because it's not like, I'll probably date myself. It's not like you're opening up Delphi or you're screwing around, or it's not like you're just powering up your PC and just writing this stuff, because it's like a supercomputer. I'm imagining it does not run on a Microsoft or an iOS.
No, that's
system.
Right. Yeah.
So what all goes into that?
Yeah. So So the supercomputer we have here at Ames is called Pleiades, and it has its own building that takes up this whole entire. It's like a city block essentially, and it even has its own cooling tower. It's so big. Why do we have supercomputers? Well, number one, all of the data that we need to understand the global system could not fit on a smaller computer, on a desktop computer.
Yeah.
But then also the computations that it takes, if we were to try to do it on a desktop computer, it would take 3 years or something
for
like
it to
that.
render
or just to run all of the calculations on all of the data. And so it's essentially impossible on a normal computer. But then if you write it correctly and you utilize the architecture of the supercomputer, then maybe it will take a day or something like that.
Okay.
So essentially a supercomputer makes impossible calculations possible now.
Oh, wow.
But so it's not like just normal programming when you're programming on a supercomputer.
You're an HTML. You're screwing around.
Right, yeah. So, often I think scientists who have not worked with supercomputers, they will think, okay, I have this little model and it works well on studying, let's say, forests, and it works well on like a watershed or just one particular forest. Well, shoot, if I just have access to the supercomputer, I'll just run it on the supercomputer and
do
boom.
your supercomputing magic.
Yeah, and then boom, I have like a whole global simulation. But that is not how it works. I guess I kind of liken it to if, you're chopping wood and you're stacking wood, okay?
Okay.
If you have a little bit of wood, you can do it yourself and it's fine. You chop wood, you stack wood. But now let's say I give you a huge warehouse full of wood, and I tell you I want one big stack of wood. And I say, but I'll also give you as many people as you want. I'll give you 1 million people if you want 1 million people. Well, okay, it's not, if you just say everyone cut and stack
Everybody
wood.
start brute force.
Right,
Let's
you don't know where the wood's
cutting.
going. Everyone cuts wood in different ways, whatever. It doesn't work. Now all of a sudden you need to organize the workers. You need to maybe put some of the workers chopping wood, some of the workers moving wood, some of the workers stacking wood, and you need somebody organizing the stack of wood, things like that.
Let alone lunch breaks and payroll.
Right, yeah, those sorts of things. So anyways, the point is that, the end goal is the same. Cut wood, stack wood.
Yeah.
But since the scale is so different and you have so many workers, the whole process chain is completely different. It's the same with supercomputing. You have a small process and the end result is the same, but just on a bigger scale. But getting from A to B is a completely different story.
Excellent. So, you're working as the fellow. You finished your PhD, right?
Yeah, I finished my PhD.
So now this is the postdoc.
This is the postdoc, right?
So what do you see in the future? What are you hoping to work on, down the road?
Yeah, so I hope to either stay on here at NASA or go on and become a professor or something.
Okay.
You know, I like teaching as well. I like mentoring, so I don't know, we'll see. But I think that's part of the postdoc experience is really understanding where you want to go with your next steps of your career.
Excellent. So for folks who are listening who have questions for Adam, we are on Twitter at NASA Ames, and we're using the hashtag NASA Silicon Valley. So questions come in, we'll loop them on over to you and see if you can get some answers back and forth.
Yeah, that'd be great.
But thanks for coming on over.
All right, thanks.